Hello everyone, welcome to my video on logarithmic differentiation. So before we start, let's remind ourselves of some properties that we use from logarithms. I'm not going to write all of them, just the ones that are most likely to show up. So the first one that we have is the fact that if we have the logarithm base a of x times y, so we have a multiplication inside the log, it turns into two logarithms with an addition. So log of a of x plus log base a of y. Okay. The second property is division. If we have log base a of x divided by y, we have a division within our log. This turns into two logarithms with a subtraction sign in between. So log base a of x, the numerator, minus log base a of y, the denominator. The final property, and the most important one, I'm going to put a star next to this one you have to know, and it's one of the reasons that we like logarithms, is the fact that if you have log base a of x to the n, you have an exponent in on the base x. We could rewrite this by dropping the exponent in front and working with multiplication. So instead of working with exponents, we're working with a multiplication. So the n in the exponent drops down in front, becomes n times log base a of x. Okay, so this guy here just drops down in front. We're allowed to do this. So let's go ahead and look at the strategy to solve logarithmic differentiation problems. So for the strategy, to step one, the first thing you do is you take ln on both sides of the equation. You could take log, but I strongly encourage you to use ln instead, because the derivative of ln is easier to work with than the derivative of log. Okay, so begin by taking ln on both sides, the natural log on both sides of the equation. That's step one. The second step is to simplify using your logarithmic properties. So let's write that, simplify using your log properties. So depending on the problem that's given, it's gonna be a combination of these three over here, typically these three here. So we're gonna simplify using log properties. 3, we are going to derive both sides of the equation using implicit differentiation. Both sides of the equation. Let me add with respect to x, just to clarify. And the final property is same as implicit differentiation. We're gonna isolate for the y prime. Isolate for y prime. Or if you use the notation dy dx. Okay, so this is our strategy. This is the procedure in order to solve logarithmic differentiation problems. So in this example here, it's asking us to use logarithmic differentiation to derive this function, y equals x to the exponent of cos of x. So how do we know we have to use logarithmic differentiation? So the key aspect to identify is the fact that you have a function in the base and you have another function in the exponent. Okay, so be careful, because if we have something like 2 to the x, the function is x in the exponent, that's fine, but the base is a 2, that's a constant. We have a rule for this. Here you would have to use the property a to the x, or the derivative of a to the x is equal to a to the x times ln of a. So we have a property. You don't use logarithmic differentiation. It's still going to work, but you're just taking more time than you have to. Okay, so we actually have a rule for this, so be careful. You're using logarithmic differentiation when you have a function in the exponent and a function on the base. Okay, that's what you should keep in mind. So let's go ahead and solve this. So recalling our steps from before, we have the first step is to take ln on both sides of the equation. So step 1, we begin by taking ln on both sides. We get ln of y equals ln of x, x exponent cos of x. Okay, so if this is equal, then this is equal. We just took ln on both sides, nothing wrong with that. What's the next step? Well, now is when we have to simplify using our logarithmic properties. Okay, so which one are we using here? What you have to notice is that we have cos in the exponent. So what we could do is take the cos of x in the exponent and drop it down in front. We're using the third property that was mentioned. Okay, so we have cos x in the exponent, we drop it down in front and it becomes a multiplication. So ln of y, so this would be step 2, is equal to cos of x, I'm dropping it, multiplied by ln of x. So instead of working with something in the exponent, we're working with a multiplication, a lot easier. And now, step 3 was saying to take the derivative on both sides. So we're going to derive both sides with respect to x. So let's start off with the left side, because what's nice about this is on the left hand side, you're always going to have ln of y. So the answer we get here is always going to be the answer. So don't memorize it, just make sure you still understand the concept. But at the end of the day, the left hand side, you always get the exact same equation. So we have to take the derivative, let's write it down. The derivative with respect to x of ln of y. And we're going to take the derivative on the right hand side of cos x times ln of x. So the derivative of ln of y, first of all, we're deriving with respect to x, and there's a y here, so this is why we're using implicit differentiation. And next, we have to recall the derivative of ln of x. So to derive ln of x, we know it's 1 over x. Or think of it as 1 over whatever's in the bracket. So this gives us 1 over y, because in the bracket of the ln it's a y. And then we have to apply chain rule, because instead of x we have a y, and we're deriving with respect to x. So chain rule says to multiply by the derivative of whatever's inside the bracket. So you get times y prime. So on the right hand side, you're always going to get 1 over y times y prime. It always works out that way. Okay. So that's the left hand side done. Let's focus on the right hand side. The right hand side of the equation, we're taking the derivative with respect to x. And the functions we're working with is cos x times ln of x. So they're both in terms of x, so we don't have to use implicit differentiation on this side. We could just derive normally. What you have to catch here, and this is super important, there's a product. It's a multiplication of two functions. We have to apply product rule. So recall product rule, let me write it up here, f times g. You're multiplying two functions. That's equal to the derivative of the first times the second plus the derivative of the second times the first. Okay. So let's start off by deriving cos. The derivative of cos we know is negative sine of x. We're going to multiply by the second function, ln of x, separated by a plus, because it's product rule. Now we're going to take the derivative of the second function, so the derivative of ln of x, giving us 1 over x, times leaving the first function as is, cos x. Okay. That's good. So this is step 3. We took the derivative using implicit differentiation on both sides of the equation. The last step is to isolate the y prime. So let's solve for y prime. How do we do that? Well, it's being divided by y. How do we get rid of that? You're going to multiply both sides by y. So multiplying both sides by just y, not y prime. The y's here are going to cancel, leaving us with y prime. And on the right hand side, we're going to have y times negative sine x ln of x plus cos x over x. Okay, so I left a bit of space here just because I don't have enough room. But if you stop here, this is incorrect. This answer is wrong. Why is it wrong? When we're taking the derivative, we started, y here was expressed as in terms of x. Y equals x to the exponent cos of x. But when we finished, we have x's and y's. We don't want that. We have to have everything written, expressed in terms of x. How do we fix that? Well, the thing to catch here, let me put this actually in brackets, because this should be in brackets. Y is multiplying the whole thing, not just the first term. We have to replace y in terms of x. But thankfully, we know what y is equal to. Go back to the beginning. We've seen this idea earlier in previous videos, that we go back to the original function. So y is equal to x cos x. So here, instead of writing y, we're just going to write what y is equal to. It's equal to x cos x. X exponent cos x. So x exponent cos x times this whole thing is the correct final answer. So having seen the previous example, try to do this on your own. Example 2, use logarithmic differentiation to derive the function y equals x squared minus x, all that to the exponent ln of x. So let's go ahead and do that. So step one, we introduce ln. We take ln on both sides of the equations, giving us ln of y equals ln of x squared minus x to the ln. Sorry, ln of x. Next, we apply our log properties too. So the left-hand side stays as ln of y. The right-hand side, we're going to use property 3, where we take whatever's in the exponent and we drop it down in front and it turns into a multiplication. So ln of x, so just be careful with all the ln's. It looks a bit confusing, but just keep track of what you have. We drop what's in the exponent, ln of x, multiply by ln of x squared minus x. Now we're ready to derive implicitly, so let's take the derivative on both sides. I'm going to use prime notation. Just keep in mind that we're deriving with respect to x. So the derivative here of ln of y, we saw it earlier, stays the same. So the derivative of ln of y is 1 over y. And thanks to the chain rule, because we're deriving with respect to x, we multiply by y prime. And the left-hand side, we have, again, a product rule. So let's apply product rule. The derivative of the first times the second, plus the derivative of the second times the first. So the first function we have is ln of x. Its derivative is 1 over x. Here we don't have to multiply by y prime. Remember, we're deriving with respect to x, and there's all x's here. So we're okay. Times ln of x squared minus x, plus, now the first one we leave, ln of x, and we take this, the derivative of the second term, times 1 over x squared minus x. Okay. So if you stopped here, be careful. You're falling for a trap. So we have 1 over x times ln of x squared minus x plus ln of x times 1 over x squared minus x. When you take the derivative of ln of x squared minus x, you have to apply chain rule here. So we have chain rule because it's not ln of x, it's ln of something, x squared minus x. So we took the derivative of the ln, we dropped whatever's in the bracket, but we have to take the derivative of what's in the bracket. Okay, so the derivative of x squared minus x is 2x minus 1. Okay, so don't forget that, don't fall for these traps. Essentially, you're always using chain rule, because when you're doing the derivative of ln of x, what you're really doing is the derivative of ln of x is 1 over x, and then you're multiplying by the derivative of what's in the bracket, x prime. So you get 1 over x times x prime. And what's the derivative of x? Well, it's 1. You're just multiplying by 1. That's why we don't write it. But at the end of the day, you're always technically using chain rule. So with that being said, let's continue. Let's go ahead and solve for y prime. We finished deriving, so step 4, isolate y prime. So y prime equals y. I'm just going to multiply the y right away because you always end up just multiplying. Open bracket. On the left-hand side, we get ln of x squared minus x, all that over x. And on the right-hand side, we have plus ln of x times 2x minus 1 over x squared minus x. Okay. So again, if you leave your answer here, it's not correct. We have to express this entirely in terms of x, so we have to substitute the y. What's y equal to? Go back to the beginning. Y is equal to this whole thing. So you're gonna have to write the answer as y prime equals, instead of writing y, we're substituting it in, and it's x squared minus x to the ln of x times whatever's in the square bracket. Over x plus ln of x, 2x minus 1 over x squared minus x. Okay, and this is okay. You can leave your answer like this. If you want, you could get a bit more technical and find a common denominator and then work it in with this, but this for me is good enough. So in this next example, we're asked to use logarithmic differentiation to derive this function over here. Y equals the square root of x plus 1 times x plus 3 squared, all that divided by x squared plus 1 to the 5. But wait, this doesn't satisfy our condition. Didn't we say for logarithmic differentiation, we need a function to the exponent of another function? Well, that's true, but logarithmic differentiation is useful for these types of problems as well, because instead of using quotient rule and product rule and chain rule all in one problem, using logarithmic differentiation actually works in this case, and it's a lot easier to do it that way. If you want to use quotient rule, you'll get the same answer, that's fine. But here's an example where we could actually use log differentiation to solve this problem. So let's go ahead and do it. So the first thing I'm going to do is rewrite the square root as exponent 1/2. And let's go through our procedure, the same steps. Step 1, we're going to take ln on both sides of the equation. So we get ln of y is equal to ln of this whole thing. X plus 1 to the 1/2 times x plus 3 squared, all that over x squared plus 1 to the 5. Okay. Step 2, we simplify using our log properties. So which properties are we using now? Well, now we're using a combination of the first and the second. If we have a product and if we have a division, what do we do with the ln? Well, here what we have is on the numerator is a multiplication, on the denominator is a division. So on top we're going to add, and on the bottom we're going to subtract. Okay, just be careful with the order of these things. Usually do the division first. Like I would do this in 2 steps. Start off with the division, do the log of the numerator minus the log of the denominator, and then after do the multiplication on another step. I'm just going to do them all in one shot in this case. But in general, do the division first. So we have ln of x plus 1 to the 1/2 plus ln of x plus 3 squared minus ln of x squared plus 1, all that to the 5. Okay. Next property that we're using is, again, we're using property 3. We have to take everything that's in the exponent and drop it. So let's go ahead and do that. So ln of y equals 1/2 ln of x plus 1 plus 2 ln of x plus 3 minus 5 ln of x squared plus 1. Okay. So although this may look longer, I'm telling you that using quotient rule and product rule and chain rule in this problem would have been even longer than this. So here we haven't even derived yet, we just set ourselves up. Now that we're at this stage, we finished simplifying, we're ready to take the derivative using implicit differentiation. So this is our step 3. So on the left hand side, it's always the same. Derivative of ln of y with respect to x is 1 over y times y prime. We always get that because of chain rule. And now let's take the derivative of each term individually. We have the 1/2, so the 1/2 stays. The derivative of ln of x plus 1 is 1 over x plus 1, okay, plus 2 times 1 over x plus 3 minus 5 times 1 over x squared plus 1. Okay. So if you got this, be careful. You made a mistake. This is wrong. Okay. Don't fall for these traps. When we took the derivative here, ln of x plus 1 is 1 over x plus 1 because the derivative of ln is 1 over x, or 1 over whatever is in the bracket. So 1 over x plus 1. But then what we did is we applied chain rule here because it's not an x, it's an x plus 1. But when you're doing chain rule here, you get the derivative of x plus 1 is just 1. So we multiplied it by 1. That's why I didn't write it. Same thing for here. It's ln of x plus 3. It's not x. So we have to apply chain rule. It's a composition of functions. And when you take the derivative of the inside, you get 1. We don't have to write it. So this is fine. But this term here, we have in the bracket x squared plus 1. We have to take the derivative of the inside. The derivative of x squared plus 1 is not 1. It's 2x. So we have to multiply by 2x. Don't fall for these traps. Be very careful. Okay, so now next step, we're at step 4. We have to isolate for y prime. Let's go ahead and do that. 4. So y prime equals, so to isolate the y prime, it's being divided by y. You could write this, instead of 1 over y times y prime, this is the same thing as writing y prime divided by y, right? And we're going to just, since we're dividing by y, we're just going to multiply it up here. We're essentially cross multiplying. So I'm going to put the y, and we know the trick now. I'm not going to leave it as y. We know what y is equal to, this whole thing. So let me go ahead right away and not write y, and I'm just going to recopy this thing, giving us x plus 1 to the 1/2 times x plus 3 squared, all that divided by x squared plus 1 to the 5. Okay, so that was just the y that was multiplied here. So we have our y that's done, x squared plus 1 to the 5, and then in brackets here we have everything that's left over. So the first term here is 1 over 2 brackets x plus 1, plus here we have 2 on the numerator over over x plus 3, and then lastly we have 5 times 2 is 10, so 10x over x squared plus 1. And now we're done. So in earlier videos we showed that f of x, which is equal to x to the n, its derivative is equal to nx to the n minus 1. This we called power rule. I proved it using a property. But let's go ahead and prove it using logarithmic differentiation, and we'll also prove the ones that we didn't show, that we just assumed to be true up until now. So let's go ahead and do this. So if f of x is equal to x to the n, let's prove its derivative is n times x to the n minus 1, where n is any value. So proof. We have y equals x to the n. We begin step 1 taking ln on both sides. Step 2, using our log properties to simplify this. So in this case here we have an exponent n, let's drop it in front. So step 2, ln of y equals n times ln of x. Next, we take the derivative of the left and right hand side using with respect to x. So this is step 3. So the left hand side, as always, we always get our 1 over y times y prime, and that's equal to, here we're going to take the derivative. So n is just a constant, it's a number, so we'll just leave it, n. And the derivative of ln of x, we're deriving with respect to x. Let me state that we're taking the derivative. I'm just going to add that, d dx. And the left hand side here, let's just write it down, d dx. We're taking the derivative with respect to x, ln of x. So we get our constant, and then the derivative of ln of x we know is 1 over x. Okay. Final step for logarithmic differentiation, we isolate for the y prime, or dy dx, depending on how you solve it. So we multiply by y times n divided by x. So the y comes on top, we're multiplying with n, and we divide it by x. But what's y equal to? So we go back to our initial statement, y is equal to x to the n. So x to the n times n divided by x. Okay, and we're done. But wait, didn't we say that the derivative is n times x to the n minus 1? Yeah, this is equivalent, because the exponent here of the x on the bottom is 1. And it has the same base as the x over here. And whenever we have our same base and we're dividing, we subtract the exponents. So n minus 1. This could be rewritten as n in the front times x to the n minus 1. And that's our derivative. So the next one that we have is that f of x is equal to e to the x. This implies that f prime of x is equal to what? What's the derivative of e to the x? Well, we showed this in a previous video. We saw that the derivative of e to the x is equal to e to the x. We used the limits, but let's go ahead and see the difference and solve it using logarithmic differentiation and see how much easier it is to prove. So we start off with y equals e to the x. Step 1, introduce the ln on both sides. So we get ln of y equals ln of e to the x. Step 2, use log properties to simplify. So essentially here we have the exponent, we take what's in the exponent, drop it in the front, giving us ln of y equals x times ln of e. So this is another property that I didn't mention, but essentially if you have log base a of a to the n, it's equal to n. So if the base of the logarithm matches the base of whatever's inside, then the answer is the exponent. That's what we have here. ln is the natural logarithm. So let me write it this way. Just a side note, ln of x is equal to log base e of x. So when we say ln of e, then that means ln of e is equal to log base e of e. And since the base of the log matches the base of what's inside, the answer is the exponent. So this whole piece here is just equal to 1. Okay, so that's another log property that we had to know for this proof. So what this gives us is 3. We're ready to take the derivative. So we have ln of y equals x. So we're going to take the derivative with respect to x on both sides. Derivative. So the left-hand side, we're taking the derivative. We know the answer to this, ln of y, deriving it with respect to x, gives us 1 over y times y prime. And the right-hand side, the derivative of x with respect to x, very simple, it's 1. So y prime is equal to y. When we multiply the y over here, we're cross-multiplying essentially. And what's y equal to? Well, go back to the beginning. Y is equal to e to the x. So we just showed that y prime is equal to e to the x, and we're done. Okay, very simple. Let's keep going. So now we have the function f of x equals a to the x, and we're looking for its derivative. So this one here, I actually just gave it to you without solving it. We're going to use logarithmic differentiation to actually prove it this time. So the first step, as always, y equals a to the x. We replace our f of x with y, and we use logarithmic differentiation by taking ln on both sides of the equation. So it's essentially the exact same thing that we saw with e to the x, but now it's just a to the x, where a is any number. Let me state that a is a constant. A belongs to the reals. Now what we do is we use our log properties we get ln of y equals x times ln of a. So same idea, we drop the x in front, that's our property, that's what it tells us to do. 3, take the derivative on both sides. So let me just write prime. We're deriving with respect to x, giving us 1 over y times y prime due to chain rule. And on the left hand side, ln of a, since a is just a number, ln of a number is just another number. So ln of a is a constant, so we're just going to leave it in the front. And what we're doing is we're taking the derivative of x, which is 1, so times 1. Okay. Step 4, solve for y prime. So multiply by y, giving us y prime equals y times ln of a. Well, what's y equal to? Come back to the beginning. Y is equal to a to the x times ln of a. And this was our definition. The derivative of a to the x is a to the x stays the same times ln of whatever's in this bracket. Okay. I put absolute values just to be more explicit, but we know for logarithmic functions, it's defined for all positive values. So now we're going to prove that the derivative of ln of x is equal to 1 over x. So this one doesn't require logarithmic differentiation, but we use logarithmic differentiation to prove the derivative of e to the x and the derivative of a to the x, which is what we're going to use to prove this statement here. So we begin by stating that y equals ln of x. So I'm replacing my f of x with y. And from this, we're going to change this, which is in logarithmic form, to exponential form. We've seen this formula, we used it in high school. It's called Napier's formula. So it looks something like, here, y equals log base a of x is equivalent to saying a to the y equals x. This is another log property you have to know, Napier. Well, it's a definition. This is how you convert from logarithmic form to exponential form, and back and forth. So we have it right now in logarithmic form. We have y equals ln of x. Well, let's switch it. We know that ln of x is the same as log base e of x. That's the base. So we have it right now in this form. So if you want, we could rewrite this as y equals log base e of x. This is the form that we have here, except that instead of having an a, we have an e. So to convert it, the e comes here. This is equivalent to the base comes here. The x that's inside ends up being alone on this side, and the y over here ends up being in the exponent. Okay. So if you're following this formula, that's how you can do it. The way I think of it is you're essentially just raising both sides of the equation to the e. But at the end of the day, it's the same idea of using Napier formula. If you want to memorize that formula, it's all right. So the way I think of it is that you're just essentially raising this to the e. So you get e to the y equals e to the log base e. These are two methods of doing the same thing. And here, this is another log property that you have to know if you do it this way. That the base here matches the base of the log, which is in the exponent. So the answer is just what's inside the log. So you get e to the y equals x. Okay. So that's two ways of getting the same answer. We have e to the y equals x and e to the y equals x. You can use whichever method you want. So I want to show you both. I think Napier formula is probably going to be the one that students prefer, giving us this. Okay, now that we have e to the y equals x, we could solve this implicitly. So we have an equation written in terms of two variables. Let's derive both sides with respect to x. So the left-hand side is the harder side. Let's do this one. The derivative of e to the x is e to the x, but instead of x in the exponent, we have y, and then we have to multiply by the derivative of what's in the exponent, giving us times y prime. Right-hand side, derivative of x is just simply 1, and what we have to do here is isolate y prime. That's the last step. So divide both sides by e to the y. So y prime equals 1 over e to the y. Okay, but we want the derivative expressed solely in terms of x, no y's. How do we do that? Well, recall that e to the y is equal to x. So we just show that the derivative is equal to 1 over x. And this is what we've been using. So here we have the function f of x equals log base a of x, and we're going to show that its derivative is equal to 1 over x times ln of a. So we stated this already, we haven't proved it, so let's go ahead and prove it. So we begin the same way. We let y equal log base a of x, and we use our Napier formula to rewrite this in exponential form. So you can use the Napier formula, or you could raise both sides to the a. I'm going to raise both sides to the a, giving us a to the y equals a to the exponent log base a of x. Okay. Since the base of the exponent matches the base of the log, the answer is what's inside the log, which is x. So we get a to the y equals x. So next we're going to take the derivative on both sides of the equation with respect to x. So d dx of ay equals d dx of x. So the left hand side has a y involved, but we know the derivative of a to the y. We proved it. So a to the x, the derivative, is a to the x times ln of a. So what we get here is a to the y times ln of a. But since we're deriving with respect to x and there's a y, we have to multiply, because of chain rule, times y prime. Next, we do the right hand side, which we're deriving with respect to x, just x, giving us 1. So we solve for y prime by dividing by a to the y times ln of a, giving us y prime equals 1 over a to the y times ln of a. Lastly, we don't want to express our answer in terms of y, we want to only express our derivative in terms of x. And this is where we apply the fact that a to the y is equal to the x. So we're going to replace a to the y with x itself, giving us 1 over x times ln of a. And this is the derivative we wanted to show.